Hello everyone. So today we'll be discussing comparators. So comparators, it describes, it's in the name. So it uh, compares to binary values, right? And that binary value can be a 1 bit, binary value 2 bit, 3 or 4, and so on. So it can be as many bits at once. So let's just start with a simple comparator. You can say 1 bit comparator, and in every like a digital system circuit, or if you are given a scenario, we always start with a truth table, right? So let's just start with a truth table here. So we have input A and input B, and this is just 1 bit, so we'll have either 0 or 1, right? Then we will check for where A equals B, where A is bigger than B, and where A is less than B, right? Let's just do the truth table. Okay, so let's start. And where we see, let's say, for example, where we're looking for A equals B. So we see A is 0, B is 0, so we write 1 here. Here we see A is 0, B is 1, so they are not the same. We write 0, 0 and 1, right? So that's our truth table where A and B is the same. Then we come to A bigger than B. So we look for A is 0, B is 0. It's not that. A is 0 and B is 1, not this. So we see A is 1 and B is 0, which is bigger than B. So we write 1 here and we check again. So in comparators, we just uh, check for these three conditions where A, B equals, are they the same, or A is bigger than B, or A is less than B, right? So here we are looking for if A is less than B, and we see A is 0, B is 1, so yes. Here no and no. So as you can see, we have made our truth table, right? Where A equals B, A bigger than B, and A less than B. It's a 1 bit binary comparator. So now let's do the uh, logic circuits, right? So if we check for A equals B, and you look through the truth table, you will find that for A equals B, this represents a exclusive NOR gate. So if you think about it, it's the negated version of no exclusive OR gate, right? So it will look something like this, right? And if you draw its truth table, if you do remember it, we can just say output here, our x, when it's 0, 0, when it's the same, we'll have 1, when it's 0, 1, 0, 1, 0, it's 0, 1, 1 is 1, right? So as you can see, our exclusive OR gate shows it can be used as a comparator to see which values, if they are the same or not, or the bits if they are the same, right? But for our, let's just say, can yeah, down here. For A bigger than B, we have to do a corner map for that. And it's much easier. Like first you do the truth table, then the corner map. Makes your life easier, it and you don't make any mistakes also. So we have our corner maps because it doesn't, if you look at the output, it doesn't relate to any truth table, right? So, or any logic gate, if we have seen, so we'll have to do a corner map to get the logic equation for this. So we said it's 0 here, it's 1 here, and 0 there, and 0 there, right? And then if you remember your rules for corner map, we only have one value, so we circle around one value where we have A is high and B is low. So our equation for this will be A not B. So you can say the logic representation of this will be, we'll have a NOT gate here, then our AND gate. So we'll have our A and B, and the output will be A bigger than B. Then we do the same for A less than B. We make our K map. We have our B here, A there, 0, 1, 0, 1. Right, then we check where A is 0 and B is 1. We have 1 here, rest is 0. And we circle around, we make a square around that. So the equation for this will be A not B. So our logic circuit here will be not A and B with the AND gate, right? So as you can see, we have three logic circuits for three different conditions. And this is what the comparator does. It checks for these three conditions where, again, the comparator is only checking for these three conditions where A equals B, A bigger than B, A less than B. And then you can combine these three circuits to form one big circuit. So we can have our A and B here. And just remember, this is a 1-bit comparator, right? So here we'll have our first diagram, let's just say not A and B. So this one is representing where A is less than B, right? Then we can have our exclusive NOR gate. So just make A on the top and B at the bottom. This checks if A equals B, right? And then our last one will be where A is bigger than B. Then we'll have our NOT gate there, and this one will give us A bigger than B. So this you can say our 1-bit comparator, right? So this is our 1-bit comparator, and we can do the same with 2-bit comparator, two numbers. Well, let's see how can we do that. So now let's just say, now we'll check for a 2-bit comparator. And then we do the same. We do the truths table, and let's say we have a number A and a B, right? So we will have our two inputs A1, A0. We are comparing with B1 and B0, right? And then we are looking for A equals B, A bigger than B, and A less than B, right? Then we'll have here 0, 0, uh, going to be then 0, 1, it's going to be 0, 0, 1, 0, 0, 1, 0. And just remember, when we do the truths table, we're just following the rule of 0, 1, 2. So you take this whole as a 4-bit binary number. But then when you do the comparison, we are separating it. So we are comparing only A and B. But just for the number sake, we do it like this. So we go up until we have 0, 1, 0, 0. Then we have 0, 1, 0, 1, and so on until mm, and so on until we have 1, 1, 1, and 1, right? And then we do the same. We now here we check for which values are the same, right? And which are less than or greater than. Then you write one like here, A1, A2, 0, 0, so that is the same. In sorry, in this case, 0, 0, and 0, 1 is greater, so A is less than B. You write 1 there, then 0, 0 again. You write 1 here, you write 1 here, right? Then you see A is greater than 1, so you write 1 here. So this is going there, and so on. So as you can see, you do the truth table again, you follow the same process. Then you do then your next step will be you do the K-maps, and then you get your equations, right? I think so equations for A bigger than B and A less than B is a big equation, and the circuit diagram is also big, so, which you can work out. But I'll show you the one for A equals B. So A equals B is something like this. So again, it's for 2 bits where A equals B. So it will look something like this. We have our A0, B0 input, then exclusive, NOR gate, right? That gives us our one comparator, then we'll have our second one, which will be here A1 and B1. So as you can see, we are comparing the A0 with B0 and A1 with B1. And then if both of them are the same, we'll have one here, one there, then that goes through a AND gate, and then we get our output where A equals B, or you can expand it just to see B1 and B0, right? Just to check equal. And checking if the numbers are equal, it's very simple. Then for example, let's say if you want to If you want to check 3-bit number, like let's just say A0, A1, and is if they are the same as B2, B1, and B0, you just add another exclusive OR gate. So that will be something like this. Then you will have here 3 exclusive OR gates. There you go. Then here you will have your A0, B0, A1, B1, then A2, B2 number. Right, and then you will have your AND gate here. And let's just your AND gate, and then your output A equals B. And for those who are confused over what is A0, B, A1, and A2, so let's just say if we have a number like 110, so I call this A0, A1, and A2. And this is a 3-bit number, right? And the same goes, let's say if we have B101, we call this B2, B1, and B0. So this will be your LSB, and this will be your MSB. And the same goes for A0, A1. So LSB and MSB, right? So that's your 2-bit comparator or even a 3-bit comparator. Now let's say if we want to have a 4-bit number, and as you can notice, even our circuit diagram is also getting bigger, right? So to represent a comparator, we use this block diagram, and you will see you have in your notes, um, you have this 4-bit comparator. So we can say this 4-bit comparator. It looks something like this. You have your block here, then you have your output A0, A1, A2, A3, right? And again here you have your output B0, B1, B2, and B3. Then there are inputs you get, which you can say they look something like, I think it's A bigger than 0. Let's just go down. Yeah, A bigger than B, A less than B. So we have our input A bigger than B, A equal to B, and A less than B. So that's our input, then our output is also the same. A bigger than B, A equal to B, and A less than B. So this is your 4-bit comparator, which most of the time you have it in IC form, and its name is 74LS85. So you can look for it. You should have it in your component 74LS85. So this is your 4-bit comparator, right? And now let's just say, for example, let's do maybe some few examples. Okay, so let's say we want to compare these 4 numbers. We want to see A01, which is, let's just say it's A, and then 1001, which is B, right? And they ask you to represent the output using the diagram. So first you have to draw the diagram, right? So let's just draw our diagram here. Comparator. So we'll have our A0, A1, A2, and A3. So just remember A0 is this, our LSB, and even here. Then we'll have A bigger than B, A equal to B, A less than B. Right. Then we have B0, B1, B2, and B3. And sometimes when we are doing the logic circuit, so this one is for the input when we are, you can say cascading. So this is used when we are cascading. So most of the time when we are not cascading, this goes to 5 volts and the other two we connect it to ground, right? And also remember, when you are doing the logic representation of the circuit, always make sure your 1 is 5 volts and your 0 is 0 volts. So in this case, to represent 1 0 1 1 0 1, so let's just say we have 1 here, 0 1 1. So these three will connect to 5 volts, right? And then our A1 will go to ground. So that represents 1 0, and same goes here. I'm sorry for my diagram. I think so it's not looking good, but yeah, hope it makes sense. So then we had 1 0 0 1, right? So our 1 will go to 5 volts. These two, we can just say 5 volts, and then these two will go to ground, right? And then we'll have our output AB, A equals B, and A less than B, right? And then we need to see which line will be high, or where will we have 1 and where will we have 0. So if we check the value right here, in this case we can see is A is bigger than B, right? So if A is bigger than B, so we can write 1 here, the others are 0. So our output will be high here and the others will be 0. Right, so it's one of the way where like you use 4-bit comparator to compare the values like this. And there's another one you can also check is, let's say if you want to compare two 8-bit binary number, right, using 4-bit comparators. And if you remember from the adders, uh, we cascade or we are connecting two comparators in parallel, right, to measure 8-bit number. It's the same thing we did with adders, where we had 4-bit adders to two 4-bit adder to add two 8-bit numbers, right? So we do the same here. So we have our comparator, and just remember whenever you draw the logic circuit, You're labeling it properly with where it should be high and where it should be low. Right. Then we'll have our A0 to A4. A, sorry, A3, A1 and A2. Then B0, B1, B2 and B3. That will be our output. Alright. And then again we know these two go to ground and this goes to 5 volts. If I'm correct, let me just confirm. Yeah, when you're cascading, okay. So this again will be our A0 to A3, then B0 to B3. So again, we are comparing two 4-bit numbers, and let's just say it's number A and B. Right. Then we'll have our second comparator, and then we have A less than B, A bigger than B, A equal to B, A less than B. And here again we'll have 0, 1, 2, 3 for the A part, 0, 1, 2, 3 the B. Then we have our output A equals B, A less than B. So we put our input like so. Now we put A4, A5, A6, A7, right? And here we put our the other part B4, B5, B6 and B7. So this is our 8-bit number. Then we take our output from the first comparator and connect it to the input of the second one, right? And then that will be our output. So that goes there. So this is our first comparator, and the second one. So this is, you can say it's a cascading comparator, right? So this was our comparator. Yeah, okay. Then we are done. Thank you.